So in the previous two videos, we created this model for a building pre and post data, pre and post retrofit data, to model the energy savings that were generated by the retrofit. And we saw that the area that results from the analysis showing negative savings has to be corrected. There's an easy way to make that correction, and we'll do that first, and then we'll have a couple more thoughts about the overall validity. So in order to take the slope out, we can essentially patch the model manually. The reason, by the way, that the slope does this to begin with is that we're extending data into predicted weather of 30 or 40 degrees when none of our measured data was ever in that range. So the measured data was somewhere in the middle here between 50 and maybe 75, 70 or 80 degrees. But we're making predictions because we're looking over a whole year's worth of weather data. We're looking at data down at 30 to 40 degrees. So the model just isn't very accurate because we have no real data to base it on. So what we're going to do is go back to the original modeling and correct that. And when I look at that for the occupied hours, which are the most important, I'm going to take a look at the slopes here. Remember what we talked about? These are already almost zero, so the baseline model is not that bad. But we're going to force those to zero and recompute. And then we'll do the same thing for the default, which is the nighttime hours. Here's what those slopes look like upward here. So we're again going to force them to zero at the ends. Recompute that as well. And with those corrected models, we'll reassemble the entire model. And then we'll do the same thing for the post data. So we'll do it for the default, zero those slopes. And then we'll do it for the occupied period as well. And with both the baseline model and the post-implementation model now corrected, we'll go back and redo the normalized energy savings. The slopes are now flat here. So this does present a somewhat better approximation, but essentially what we've done is to look at the results where our measured data, meaning the temperature range over which we took actual samples, is modeled very well, and the rest of it we simply used flat slopes for the model, which just means if we are doing measurement and verification over a short period of time, which is often the case, sometimes there isn't enough time for more than 2 or 3 weeks worth of measurements, then this entire model is going to become far less accurate, because if I'm within a 60 to 70 degree range over those 2 or 3 weeks, then only this sort of center portion of my analysis will really be well modeled, and the rest will essentially be extrapolated quite crudely. So it is pretty important to ensure that when MNV data is taken, both for the baseline model and for the post model, the length of measurement is as long as possible, and the range of temperatures that gets taken is as wide as possible, because that overall will of course affect the savings number, which has now dropped to 650,000 kilowatt hours per year. It'll affect that savings number quite dramatically. But anyway, this is a large improvement in the short minutes that these videos ran here. We've examined the whole building with just a handful of input data and a very simple set of input data that is easily reproducible for a multitude of projects that allows both the engineer doing the initial savings calculation and any inspector or third party wishing to reproduce those results to also do so. So this gives us a simple tool for measuring energy performance and then calculating the savings and doing it in a uniform manner that multiple people can do independently of each other for verification of the calculated results.